Okay, your smoke alarm just went off. Loud. House on fire? Almost certainly not. I made toast. But the alarm is designed to scream when there's a fire, so why are you so calm?
Because real fires are rare, and burnt toast happens to me twice a week. The alarm going off is real evidence. It just isn't much evidence, because there's a much more boring explanation that's way more common.
So the alarm's reliability and the chance there's actually a fire, those are two completely different numbers. And this is a bonus episode, sitting right after Lecture 4 on conditional probability. We're doing total probability and Bayes' rule.
Two of the most useful ideas in the whole subject, and they're built entirely from things you already know. Let's get into how you get from one of those numbers to the other.
Here's the core split. Usually what we can measure is cause to evidence. How often does a real fire set off the alarm? That's the probability of the alarm given a fire. Forward and easy to pin down.
But what we actually want is the reverse. The alarm went off. Now how likely is a real fire? That's the probability of fire given the alarm. Same two events, conditional flipped the other way.
And those two numbers can be wildly different. Bayes' rule is the machine that turns one into the other.
And here's the punchline we'll keep hitting. A rare cause tends to stay unlikely, even after the evidence shows up. Hold that thought. It comes back twice.
Before the new stuff, 2 tools from last lecture, and that's genuinely all we need. First, conditional probability. The probability of A given B is the probability of A and B divided by the probability of B.
Rescale to the world where B already happened. And the second tool is just that, rearranged. The probability of A and B equals the probability of B times the probability of A given B. That's walking down a branch of a tree. You multiply as you go.
So hold on to both.
Total probability stacks them across many branches, and Bayes reads the tree backward. That's the whole episode, right there.
First idea, partitioning. A partition chops the sample space into pieces that don't overlap and together cover everything.
So every outcome lands in exactly one piece. Picture sorting every apple in a store by which farm it came from. Each apple has exactly one farm, and every farm together gives you all the apples.
And then some event A, say the apple is bruised, cuts across those pieces. On the slide, the blob A overlaps several of the B pieces, so A gets chopped into slivers. The bruised and from farm 1 piece, the bruised and from farm 2 piece, and so on. Those slivers don't overlap either, and that's the setup that makes everything add up cleanly.
Let's make it real with just 2 cases. A café gets its muffins from 2 bakeries. Bakery 1 makes 70% of them, and 10% of those go stale. Bakery 2 makes the other 30%, and 20% of those go stale.
Pick a muffin at random. What's the chance it's stale? You walk down each branch and weight it. The probability of stale is the probability of bakery 1 times the stale rate there, plus the probability of bakery 2 times its stale rate.
So plug in. Down the bakery 1 branch, 0.7 times 0.1 is 0.07. Down the bakery 2 branch, 0.3 times 0.2 is 0.06. Add them, 0.13.
Multiply down, add across. That's the law of total probability. Really just a weighted average of the rates, weighted by how common each case is.
Same move works for any number of cases. If the events B1 through BK partition the sample space, then the probability of A is the sum over every branch of the probability of BI times the probability of A given BI.
Old textbooks call it the rule of elimination, but total probability says what it does. It totals the event up across all the branches. Picture a tree with K branches, every one feeding into A, and each branch contributing its prior times its conditional. Add them all up, you've got the total. Now let's run the real example, the one we'll use the rest of the way. A grocery store stocks apples from 3 farms. Farm A supplies 50% of the apples, and 2% of them are bruised. Farm B, 30%, 5% bruised. Farm C, 20%, 10% bruised.
What fraction of all the store's apples are bruised? Walk down each branch and read off the tip. Farm A, 0.5 times 0.02 is 0.010. Farm B, 0.3 times 0.05 is 0.015. Farm C, 0.2 times 0.10 is 0.020.
Add the 3 tips. 0.045. So about 4.5% of the apples in the store are bruised.
Keep those 3 branch numbers on screen. We're about to use every one of them again, backward.
Here's the flip. You reach in, grab an apple, and it is bruised. Which farm did it most likely come from? Going forward, we knew the probability of a bruise given the farm. That's straight from the data.
But now we want the reverse, the probability of the farm given the bruise. The conditional just turned around.
And the key move is short. The probability of farm R given bruised is the probability of farm R and bruised divided by the probability of bruised.
And we already have both pieces. The top, farm R and bruised, is just that one branch of the tree. The bottom, the probability of bruised, is the whole tree total we computed one slide ago. That's the entire trick.
Write that out for a full partition, and you get Bayes' rule. The probability of BR given A equals the probability of BR times the probability of A given BR, all over the sum of that same thing across every branch.
And that denominator is exactly the probability of A from total probability. It's there to make all the answers across the branches add up to 1.
3 names worth knowing. The prior, the probability of BR, is your belief before the evidence. The likelihood, the probability of A given BR, is how well that case explains what you saw. And the posterior, the probability of BR given A, is your updated belief after seeing it.
Prior times likelihood, then normalize. That's Bayes in one breath.
Back to the apples. We found the probability of a bruise is 0.045, so divide each branch by that total. Farm A, 0.010 over 0.045, that's 2/9, about 22%. Farm B, 3/9, about 33%. Farm C, 4/9, about 44%.
And the add to 1. The bruised apple came from somewhere.
But look at the ranking on the bar. Farm C supplies the fewest apples, only 20%, and yet it's the most likely source of a bruised one, because its bruise rate is so high it overpowers the small supply. And Farm A, the biggest supplier, is the least likely culprit. Bayes is weighing both things at once, how much each farm ships and how often each one slips.
Now, the one that surprises everybody, a screening test for some condition is loosely 90% accurate. 1% of people actually have the condition, that's the prior. The test catches it 90% of the time, and it false alarms on 10% of healthy people.
You test positive. How worried should you be? Walk the same machine. The probability of a positive is 0.01 times 0.90 plus 0.99 times 0.10. That's 0.108. So the probability of the disease given a positive is 0.009 over 0.108, 1/12, about 8%.
If the fraction feels slippery, just count 10,000 people. 100 are sick and the test flags 90 of them. Of the 9,900 healthy people, 10% false alarm, that's 990. So 1,080 positives total and only 90 are truly sick. 90 over 1,080, 1/12 again, about 8%.
A positive result on a 90% accurate test, and there's still only an 8% chance you're sick, because the condition was rare to begin with. The base rate dominates. That's the smoke alarm all over again.
3 things to carry out the door. 1. Don't flip the bar. The probability of A given B is not the probability of B given A. 90% of sick people test positive is a completely different claim from 90% of positives are sick.
2. Base rates matter. Start rare, stay rare. A strong test can't overcome a tiny prior on its own. 1% only crawled up to 8.
And 3. The recipe. All 3 theorems in one breath. Multiply down each branch, add them up for the probability of the evidence, then divide the one branch you care about by that total. Whenever you've got a partition and the conditional probabilities, a tree turns every which cause question into plain arithmetic.
That's the bonus episode. We partitioned the sample space into cases, totaled an event across all of them, and then flipped the tree to ask which case the evidence points to. Partition, total probability, Bayes, prior times likelihood, then normalize.
And this isn't a curiosity.
Spam filters, medical screening, search and rescue, a lot of machine learning. They're all the same loop. Start with a prior, see evidence, update. Walpole picks it up again in Chapter 18 as a full method of statistical inference.
So next time your smoke alarm goes off, you'll know exactly which number to ask for.
Probably still toast. Catch you next time.